Moving right along. Okay. So now let's talk about physical and chemical changes. And so instead of giving you a lot of definitions, which occasionally I might, I like to teach through example. So here I have three pictures that could either be physical or chemical changes. And so instead of giving you definitions of these, let's see if we can't work out what a physical change is and what a chemical change is by the pictures. All right. So now if we look at this one, so again, these are all examples of carbon dioxide. So typically carbon is represented with a black atom and oxygens are represented with red. So that's not just like these cute little slides. That's pretty typical throughout most chemistry, that carbon is given as black and oxygen is given as red. So here we can see C and two oxygens. Okay, we're going to get into these subscripts in a little bit more detail. So I know some of you have had chemistry and some of you have not had chemistry at all. So don't worry, I'm not going to leave any of you behind. But now what you can see here is these are all crammed together. They're really close together. And that's indicative of something being a solid. Okay, so I put a little S in parentheses there to note that it's a solid. And so now these things, some process has happened, some change, and now these molecules are all loose and they're not very close to each other. So that would be indicative of a gas, which I'll put as a G, a little G in parentheses there, okay? So you notice the chemical composition of these did not change, so it can't be a chemical change. This has to be a physical change, okay? So, and it's a physical change of state going from the solid phase to the gas phase. And we'll talk about all of those changes of state soon. Okay, so now here we can see a bunch of purple stuff and a bunch of blue stuff, and you can see they're diatoms, right? But now look, the way that they're physically bonding with each other has changed. I know I just used the word physical there, so that's a little confusing. But all the same, because the way that these are bonded together have changed, this has to represent a chemical change. Okay? And similarly, as you can see right here, because of the way that these all red balls are bonded differently in this picture versus this picture, that also has to be a chemical change. Okay, so this is a chemistry class, but we will still very much talk about physical changes. So we need to make sure that we understand the difference between a physical change and a chemical change. Typically, a physical change involves something going from being like a liquid to a solid, or a solid to a gas, or a gas to a liquid, etc. Okay? Moving right along. Okay, so now here we are at one of our first laws. And what I really want you to respect the law, right? Respect the laws of science. And I'm going to talk a little bit about the, the scientific method, hypothesis, conclusions, results, etc., etc. I just said all of that out of order. But when we finally get to where something is a law, that means it's tried and true. It has been discovered and rediscovered over and over again, and the same idea comes out every time with these discoveries. Okay? So the law of constant composition states that all samples of a particular compound contain the same elements combined in the same proportions. So key words here are same elements in the same proportions. Okay? So for example, here's a picture of water. So oxygen is red and hydrogen is almost always white. Okay? And hydrogen was one of those things we talked about being H2, one of the diatoms. And we know oxygen is also one of the diatoms. Okay? And so now here we have water, which is two hydrogens and one oxygen. So I can write that as H2O. Respect the subscript. I'm going to write that again. Respect the subscript. Okay? The subscript means there's some bonding going on there. We don't have two random hydrogens and one oxygen. We have this symphony of oxygens, one oxygen with two hydrogens, okay? Respect the subscript. Now, if I had wrote this 2 H2O, okay? We still have to respect the subscript, okay? But now we have what I'm going to refer to as the coefficient. And so that coefficient out in front means we're talking about 2 water molecules, which means we have 2 times 2, 4 hydrogens, and 2 times 1, 2 oxygens, okay? But that doesn't mean that all 4 of those hydrogens are bonded to all 2 of those oxygens. We got to, what? Respect the subscript, okay? That subscript is super important. It means for every 1 oxygen, only 2 hydrogens can be bonded to it, as we can see in this picture, okay? And so now with this law of constant composition, if we're trying to combine hydrogen and oxygen to make water, we have to respect that these will be made up with the same proportions. So, to make 1 single water molecule, I need 1 oxygen and a half of a hydrogen, which is pretty tough to do. So an easier way to do it would be that if I combined 2 of these hydrogens, look, I'm going to put the coefficient there, plus 1 oxygen, now I've got enough material to make 2 water molecules. And as it turns out, this is a very, what I will refer to later in the semester as, I think I can do an undo, yes. This is a very exothermic reaction. Boy, I can't type with this thing or write with this thing. I'm learning. We're getting there. So we're going to talk about exothermic and endothermic reactions later on in the semester. But what that means, exothermic, it means energy is leaving. So there's an explosion when you combine hydrogen and oxygen. And hopefully I'll be able to grab myself some hydrogen and oxygen and blow it up somewhere for you and take a video of that, okay? So this is the law of constant composition. And I'm really taking my time with the slide, and it might seem kind of like a simple idea, but later on, when our chemistry starts getting a lot more complicated, I want you to go back and remember this law of constant composition, okay? Same elements combined in the same proportions. Okay, moving along.